Discussion.
Thank you very much for the nice introduction. Thanks to Chris and the organizers for inviting me to attend. It's been a long time. It's nice to be back among my MIC friends. And this is a kind of a sequel to the talk that Andrew just gave, so nicely organized on the organizer's part. So the work I'm going to present is primarily the dissertation work of Jason Hu, is a student that I co-advised with my colleague Liu Shen, who joined Michigan a year ago, as well as one of her other PhD students, Bowen Song, and a former postdoc of mine, Xiaojun Xu. All right, since it's a session that includes things about generative models, I had to ask one of the generative methods to visualize what this talk might be like, and maybe you should have invited the guy on the left, because that might have been a more entertaining presentation. Now, if you notice carefully to the words on the slide, on the picture on the right, they're spelled incorrectly, right? So I won't use the word artificial intelligence anywhere in my presentation, because I think we're a long way still from intelligence, but we certainly have machine learning methods that can learn a lot about the characteristics of images, as you can tell from these examples. So this is a little outline. I think I'll skip that. So, as we've just heard from Andrew, and probably many other times during the week that unfortunately I was unable to attend, we're interested in solving inverse problems, such as y equals ax plus some sort of noise, perhaps plus or perhaps some other operation other than plus, whether that's MRI, CT, PET, etc., where the notation here is that y is the measured data, A is our system matrix, and x is the latent image we'd like to reconstruct. And as Andrew just nicely described, in problems with a lot of noise or in problems where you've done some kind of undersampling, such as in sparse view CT or accelerated MRI, maximum likelihood estimation by itself is inadequate because it's an underdetermined problem. And even if it wasn't underdetermined, there's so much noise that you probably don't want to do maximum likelihood estimation. And in fact, in some applications like image inpainting, where you have missing elements in your sensor, the pseudo-inverse solution is actually just the original data, which is really useless. So for years, many of us have worked on handcrafted regularizers to solve this problem. And we've heard about the relative difference friar as one example of those. And in most of my publications, my group's publications, we use the term regularization rather than priors, because if you sample from the distributions associated with these regularizers, they don't look very much like the images we're actually interested in. So I was very hesitant to call them priors. And then we have other solutions, such as the ones you just heard about, such as taking some sort of initial solution and putting it through a neural network to clean it up, unrolled versions, and so on. And then there's been a long history, actually, of methods that are called Bayesian methods in our field that recently have been relabeled, I guess, as generative models. And this is a really long history. So even in my graduate student days, I was reading papers like this one by Gieman and Gieman, where they were looking at what they called Bayesian methods, priors built out of cliques of neighboring pixels, typically like 3 by 3 or 5 by 5 cliques. And when I read these papers, at least, I was mostly thinking of them as methods for inference, right? Methods for solving, basically for making up regularizers, even if they're called priors, for solving reconstruction problems. But I went back and looked at the literature as I was starting, my group was starting to get interested in generative models, and I did find some examples where people were trying to think of these priors as generative models. So this is a paper from 1994 where they were taking drawing samples by Monte Carlo methods, fairly computationally challenging, to see what samples from these priors would look like. And they looked at, like the example shown here, and they say in the abstract, commonly used Markov random fields are not, in fact, capable of representing the moderate to large scale clustering present in natural occurring images. So that paper went on to make a modified method that captured a little bit more large-scale features. Now, if you look at all these images, you notice the large-scale features all sort of go from the top left to the bottom right, and that's because the way they developed this method is they had a sequential algorithm that started in the top left and worked its way down to the bottom right, introducing correlations along that diagonal. So there's some larger-scale features here, but it's still a long way from looking like a PET or MRI or CT brain image. And they comment that the local properties of spatial Markov fields are undoubtedly plausible descriptions of the local associations typical of many images, but nevertheless it would be reassuring if the models used as priors did in fact provide a realistic representation of our prior assumptions, and if their empirical properties were known, better known. I think we've made a lot of progress, we, the generative model feeling, in making more realistic representations. I think we're probably a long way of really fully understanding their empirical properties. And okay, so you've already seen, if you just pick up the paper, that generative models are hot in graphics, they're hot in face synthesis and deep fakes and all that, even hot in science, hot in art. So it's not surprising that generative models have also infiltrated our field of inverse problems. If you haven't seen it, there's a very nice paper a year and a half ago in the IEEE Signal Processing magazine, a survey paper on a whole variety of generative models to be used for solving inverse problems. In fact, there's a GitHub catalog with hundreds of papers in this field. At the last time I looked, there was at least 20 survey papers. So even though this is relatively new, there's lots of surveys of these papers coming out. And this is already very out of date. And one of the papers that really caught my attention, in fact, was from my new colleague, Liu Shen, and her co-fellow graduate student at Stanford, Yang Song. They had this paper in iClear 2022, where they trained a diffusion model of the kind that Andrew talked about, and I'll be talking about more, with 47,000 relatively clean two-dimensional CT images. And then they used that to reconstruct from only 23 projection views, which for those of you who know who work in CT is a very large amount of downsampling. A typical sinogram is like on the order of 1,000 views. So they took those 23 views and combined it with their generative model, trained on a lot of example images, and compared it with methods that include unrolled deep learning algorithms, of course, total variation, and so on. And I don't think in this room you'll be able to appreciate the differences, but there's really impressive details when you zoom in on this image. It kind of blew me away that you could get this kind of details from just 23 projection views. However, in many of my applications, maybe most of my applications, probably yours too, you probably don't have 47,000 clean images. And of course, in the computer vision field, they're training with orders of magnitude more than that. But let's come back to that point in a second. So if the ability to learn a prior, then you can use Bayes' method, and you can do a number of things. You could maximize the posterior by doing map estimation. You could compute the conditional mean. You could sample from the posterior to get uncertainty quantification. And it looks like from all of these, what you need is the prior. But in fact, you don't really need the prior. All you need, as Andrew already alluded to, is the score function, the gradient of the log prior. Because if you have a model for the gradient of the log prior, and that model is typically implemented by a neural network, then you can put it through methods such as this Langevin dynamics stochastic gradient descent to generate samples from that prior. And this is more or less what's being done to generate some of those amazing looking images that I showed at the beginning of this talk. You have to choose, there's a number of details in how you choose the weighting functions and so on in this process. But you're basically adding noise in the appropriate amounts to samples, or to the gradient of the log prior, and you can generate samples from that distribution. Now, let's contrast the ease or whatever of learning the gradient of the log prior compared to trying to learn the prior itself, right? Typical models, as Andrew already alluded to, have this Gibbs form where you have some exponential with some energy function and a normalizing constant out front. And if you try to do maximum likelihood estimation to learn the parameters of that prior, you're going to be faced with the difficulty of having to maximize a function that depends not only on the energy function, but also on this normalizing constant, or partition function it's called. And typically that's intractable. All right, so there's lots of papers on this, but they're all very challenging, and they didn't really catch on very much because of that challenge. In contrast, if you're okay with just working with the score function, once you take the gradient of the log prior of this form, we're taking the gradient here with respect to the image, not with respect to the model parameters. When we take the gradient with respect to x, with respect to the image, conveniently, the term that involves the partition function disappears, and we're only left with the gradient with respect to the energy function. So that is the big part of the appeal of working with the score function instead of trying to model probability distributions directly. All right, so that opens up the question. If you were given a bunch of training images, in other words, clean images, hopefully reasonably clean anyway, how do you learn the score function, the gradient of the log prior? And actually, that could be a whole hour-long talk in itself. There's a whole bunch of different methods in the machine learning literature, explicit score matching, implicit score matching, and so on. But there's this thing called Tweedy's formula that relates the score function to a denoising operation. So for today, if you're not familiar with this, it's sufficient to just think of learning a score function is equivalent to learning a denoiser. And it's specifically learning a denoiser for denoising Gaussian noise added to the image. That's how the noise works out. That's how the math works out, I should say. And you might be immediately thinking, oh no, but my pet and spec images have, or my data in pet and spec has Poisson noise, but that's irrelevant. This is just for learning the prior. You put whatever physics and measurement statistics you have in the log likelihood. This part is only for learning the prior. And if you're familiar with kernel density estimation, adding this Gaussian noise is sort of like convolving all the Diracks of each of your samples, training samples with little Gaussian, so you can sort of make a smooth density estimate. That's roughly my intuition of what's going on behind this, these score matching processes. Let's see here. Is there anything else I want to say on this slide? Oh, how much noise do you add? The answer is a whole bunch of different levels of noise. You draw noise from a distribution of different noise levels and take an appropriately weighted combinations of all those. So you can think of it as convolving your true distribution with Gaussians of different amounts and combining them all together. So in fact, your neural network that you're training has input both the noisy image, this is really hard to do, the noisy image, of course, the network parameters, and the noise level. All three of those things are inputs to the network. So when you're all done, you have a noise-dependent denoising function that you've learned. And this is the picture that everybody shows in this. You start with your training images, add noise to it until you get to the point you have a totally noisy image, and it's always presented this way. Then you take it and you run it backwards, and the way these pictures are usually shown, it looks like you're getting back the image that you started with. That is not the point. You're actually trying to take these noisy images over here, run it backwards to get samples from the same distribution of the set of images you use for training. So it's not the same x0, but this is the plot that you'll see over and over in papers, and it's slightly misleading. And it takes some work. You have to run this backwards things maybe hundreds, if not thousands of times to draw good samples. People, of course, are working on that. I think that's actually my next slide. So what are the nice things about working with these generative models? First of all, they're much easier to train than adversarial models. GANs are more difficult to train than these models. And as you've seen in some of the examples, you can get quite high quality sample generation if you have enough training data. But as I already alluded to, the challenge is that it's relatively expensive to draw those samples. So anytime there's such an engineering challenge, you can imagine lots of people are working on this. So this is an out-of-date list of some of the many different ways the community is working on trying to speed up the sampling process. And so I'm not going to worry about the compute time here. In fact, my whole career has been working on things where people said it's going to be too slow to use in practice and over, including OSEM or whatever. And the field has consistently seen eventually the computing gets fast enough, the algorithm's fast enough that these things get used and get eventually, if they're useful enough, become clinically used. So I'm not too worried about compute time. Now, what I am worried about is amount of training data, right? So if I'm really interested in 3D problems, I bet most of you are too, and also dynamic 3D problems. I bet most of you are too. And trying to learn whole image or dynamic image models from a small amount of training data, I think is going to be extremely difficult. All right? The amount of training data, and even if you had enough, fitting it in your GPU memory is very challenging. So what can we do to take advantage of this wonderful new field of generative models, but manage with a smaller amount of training data and realistic amounts of GPU memory? So this is a picture from an MRI perspective, but I think the same thing applies in, say, low-dose PET. So I'll present it here from an MRI point of view. All of the trajectories, the K-space trajectories that we use in MRI, even the most fancy ones and the most basic ones, are densely sampled at the center of K-space, because that is where most of the information is, most of the SNR is at least. So the low frequency, the gross features of the image, we can always get from the measurement data itself. It's some of the high frequencies that are missing, So I don't feel like I need a whole image model. I need a generative model that will let me fill in fine details. I don't need to generate a picture of a scientist standing in front of a chalkboard like people in the computer graphics field need to do. Similar with sparse view CT, right? If you have sparse projection views, you can back project and low pass filter that, and you'll get a low resolution version of your image, right? So the gross features are there. It's the fine details that we need some help from our priors. And I think the same is true with, say, low-dose PET, right? You can do filter back projection even, or OSEM, and get a low-resolution image if you filter some or whatever, and then rely on your priors to clean it up from there. And so this is not a new comment. So if we only need fine details, we can probably model that with patches. In fact, total variation is a regularizer that just uses patches of size 1 by 2 or 2 by 1, right? That's the smallest size patch you can have, non-trivial patch size. So you would think there's a lot more information in, say, an 8 by 8 patch than there is in a 1 by 2 patch, and that every sort of hot topic in the signal processing field has been applied to inverse problems, whether it's GANs or dictionaries or non-local means and so on. Lots of use of patches in this field. So I hope to convince you in the next few minutes that patches are also useful for solving inverse problems. And I'm going to show you results that are all in 2D, but the motivation of all this work is to move to 3D and higher, where I don't think whole image models are feasible. So I'm going to do this in 2 stages. I'm going to give you a warm-up version first that is not good, but is simpler to explain, and then I'll add the bells and whistles that makes it useful. All right, so let's say we take a fixed patch size, 8 by 8 or whatever, divide up our training images into those patches with a fixed location of the grid, and sort of throw all those patches in a pile and say, okay, let's learn the distribution of those patches. I first presented this version of it in March 2023 in Switzerland. All right, so that's the picture. Mathematically, it's another Gibbs model, like Andrew was talking about, where we say our model for the whole image is a product of the models for each of the patches. This is called a field of experts or a product of experts in the Bayesian community. So what we have is a clique function, V sub x, energy function for each of the patches, and we just multiply them together to sort of assess the overall probability. And I'm going to assume temporarily here that all of the patches, this is a modeling assumption, it's not realistic, are identically distributed. So in other words, every one of these clique functions should just be the same common clique function, and this matrix G is the giant matrix that grabs the Seath patch out of our 2D image and just gives us the, say, 8 by 8 patch. So what we need to learn here is this function V, a common patch clique function. All right, so if I take that model, this product of experts over patches model, and write down its log prior, then the things simplify as shown on the top equation, and then the score function of the whole image is the gradient of that, and once I take the gradient, thankfully again, the partition coefficient goes away, and I'm left with a sum that involves the score, a patch level score function. All right, and so we extract patches from the image, we put them through this patch size score function, and then we reassemble them. This summation with the G transpose here is putting the patches back in the right place and summing them up. So we need like a tiny unit for this, whatever the size of our patch is. And now that's what we need to learn, is the parameters of that small score function, that patch level score function. And we can do this again by training a patch level denoiser, by adding various levels of noise to that. And this is the math to show that that's the right thing to do under that assumption. And again, we add multiple levels of noise to it. And I'll skip the details there. Key to this is the input to our neural network is never the entire image. It's only patches. So we can do batches of patches to whatever the size of our neural network memory is. So this approach scales to 3D, large 2D, 3D, and 4D problems. However, if you do it just the way I've described here, some of you have already thought of this, you'll get boundaries, artifacts at the boundaries between patches. And it turns out that we found empirically that using a fixed patch size slows the learning. And the assumption that all patches have the same distribution no matter where they are is unrealistic. So that was version 0.1. Let me move on now to what we actually do. And all the rest of the results will be based on this model. So first of all, we zero pad our image, so we have a little bit extra wiggle room. And then we use multiple different locations of the patch grid. In fact, in some sense, all possible locations of the patch grid. And in fact, in training, we also use different patch sizes. So we get even larger collection of grids that way. For those of you who know about wavelets, this is a little bit similar to what's called cycle spinning in the wavelet denoising literature. All right, so mathematically, that involves a larger product, a product that involves not just the patches, but also something having to do with the border and all the different positions of the grid. And there's a little bit more that we do as well. We actually give as an input to get rid of that identically distributed assumption, we also put the position of the patch into the network. We give that information, the position, and so that's shown by these extra coordinates here that are going into that function. So now we have location-dependent priors. Let's see. So we are learning a position-dependent score function. So that's a lot of math. The next slide has a picture for it. I hope you can see that even in the back. So we're taking our training images, and we're extracting patches of various sizes from it with various grid alignments. So this is just showing two examples of patches. A big patch up here and a smaller patch I can hardly see down there. But what goes into the neural network is not just that patch of the image, it's also a corresponding patch out of the X and Y coordinate grids. Think mesh grid in MATLAB or whatever. And so it's a 3-channel in our case, because CT images are monochromatic. Well, some of them are. So the image and then the X and Y coordinates. And those 3 things, we add noise only to the grayscale image part. We don't add noise to the coordinates because that's a known thing. We put that into the UNet. Out comes, the UNet is learning to denoise. Out comes the denoised, hopefully, denoised patches. And we do this over and over with as many patches as we have from our training images. I say as many as we have. We don't do it exhaustively. We're drawing random samples of patches from our training images. Even if you have only one image, there's a lot of patches in that image from which to train. And I want to emphasize this training process here has nothing to do with the imaging system. How many projection views, whether it's fan beam or parallel beam, right? This is a property of the training data set itself. And I think this is one of the key benefits of generative models, as opposed to, say, end-to-end methods, is that you can learn your prior independent of the imaging system. Of course, it depends on the contrast of the CT image. So if this was a megavoltage CT, we would need a different set of training images for that. All right, so now I'm going to show you some results, both of sampling and of reconstruction. And for training the prior, we used CT images from the APM 2016 CT Challenge. There were 10 3D volumes. We downsampled it for expediency to 256 cubed, sorry. These are slices. You can see they roughly go from the shoulders down to the abdomen. I think there were about 2,000 slices out of that set that we used for training. So 2,000 is a lot less than 47,000. I'm going to show you results from even fewer training examples later. Now, with those 2,000-ish training samples, we trained a whole image model and then drew samples from it. That's the top row. This is not reconstruction. This is just drawing samples from the learned prior. So a whole image learned prior on the top row. The middle row is that version 0.1 that I described, where the patch grid is fixed with non-overlapping patches. And then the bottom row is with the more advanced method that includes variable patch size and shifting the grids every update. Even the whole image model is not, they look kind of like CT images, and they're not super realistic because they've been only trained with 2,000 images. If we had trained these with 47,000 images, I think you'd see more realistic samples up there. But remember, we're not in the graphics business, right? I just need to be confident this is a reasonably good prior for saying what are good and bad images when I combine this with my sinogram data for reconstruction. So seeing images like this is the point at which I start to become a Bayesian, right? Instead of just talking about regularization, I'm willing to now use the prior language because these look not unlike the kind of images we're interested in reconstructing. And actually, to me, I find it amazing that by using the overlapping boundaries or whatever, remember, this neural network never saw anything bigger than a 56 by 56 patch. Yet by putting the patches together in an overlapping way, it can draw samples in that bottom row that have more or less reasonable anatomy. The position encoding helps here a lot. You'll notice that whatever this is, the spine of the vertebrae, it's kind of typically appearing at the bottom of the image because all of the training examples have the spine at the bottom. Nobody was lying on their stomach, I think, in the training examples here. And there's a little bit of 5 minutes, okay. You counted for the extra, okay, yes, all right. Once we have that prior trained, on the reconstruction side, we're not doing anything novel. It's very similar to other methods that have been used with diffusion models. It's sort of like Andrew alluded to, you go back and forth between data consistency and then putting your image through the denoiser. But our denoiser is a patch-based denoiser. At this stage, we always use the largest patch size for various reasons, but with a shifting grid every time, just like in wavelet cycle spinning. All right, so that's there's the details in flowchart form. There's the little bit more about, I think I said most of that already. I think I'll skip that. Okay, when you submit a paper on work like this, you know you have to do a lot of comparisons. And then the reviewers ask you to do even more comparisons. So we end up with a lot of rows of the table. The top row is filter back projection. And then the next row is total variation reconstruction. And then we get into a whole bunch of machine learning-based methods, and then including whole image-based diffusion here. But remember, whole image diffusion trained with only 2,000 images. And then the patch-based method at the bottom, which of course has all the bold numbers, otherwise we wouldn't be talking about it, right? So, and we've done it with CT with various number of projection views and also some other applications. I think I will skip this. Some images that you can't appreciate in this room, so I might as well move quickly past that. Now, the position encoding matters a lot. So we did an ablation study where we eliminated the position encoding. You can see the metrics drop by a huge amount. So the position encoding is really part of the secret sauce. Patch size matters too. If you make the patch size the whole image, the performance degrades because we only have 2,000 training examples, and that's not enough to train a good whole image model. If you decrease your patch size too much, performance degrades as well. Presumably you're not learning enough about the relationship between neighboring pixels. But doesn't degrade a ton, but it degrades some. And I've been showing you results trained with 2,000, but if you drop from 2,000 down to, sorry, I'm still learning how to do this, down to, say, 144, the patch-based model, it doesn't lose that much performance in terms of PSNR, whereas the whole image model drops a lot when you only have 100-some training examples. In fact, the performance of 144 training examples with patches is similar to having 2,000 training examples for a whole image model, really showing the benefit of patches for reconstruction setting. I'm not talking about generation. There's images that you can't see to show the benefits. I might as well blow by those. So, okay, Chris asked me to talk about PET. So I think the challenge you have in PET imaging is getting the high-quality training data. But actually, Simon Cherry just visited Michigan a week ago and showed me amazing-looking images from the Explorer kind of system. So you guys probably do have high-quality training images that you can use to generate your models and then apply them to, say, lower-dose scans or whatever it is that is your real application. So yeah, using total body PET is probably the way to go if you want to get really high-quality training examples. There still is an issue with out-of-distribution. What if you've trained this on FDG and you want to apply it to see something else, some other radio tracer? That's something we're currently working on. My student just submitted a paper to iClear that is on archive. This is as fresh as it gets in the last week or so, where we are using, so we train a patch-based model just with ellipsoid images, and then at test time we refine it in a self-supervised way with whatever the test data is. And it works remarkably well, way better than trying to refine a whole image model. And I think that might be to summarize, I hope I've convinced you that not only are generative models an interesting direction for our community, but that patch-based models might be particularly practical in our setting where we might not have tons of training data. And here I haven't done anything fancy in the denoiser, such as trying to have various kind of invariances. I think we could further make these models more powerful by incorporating some invariances into them. And we've already begun to explore trade-offs between generalizability and in-distribution performance, but I think there's a lot more that can be done there. And everything I showed you today is 2D, but this is all motivated by future work in 3D. In fact, one of our archive-based papers is already in 3D, so there's actually work out there where we've done 3CTD. So with that, thank you very much for your attention.